Good afternoon. We are going to present a topic titled Leveraging AI to Improve Early Diagnosis and Detection of Malaria in Uganda. This is presented to you by Joseph Yarwanga and Muhindo Mubaraka. According to the World Malaria Report 2020 compiled by the World Health Organization, around 229 million cases of malaria infections occurred in 2019, with an average of 400,000 infected people dying. Most of the victims of the malaria are children under age of 5. Malaria is mostly prevalent in African regions, contributing to 90%. This is followed by Southeast Asia, then South America, then the last is Sub-Saharan Africa. Malaria is a disease caused by a parasite. The parasite is spread to humans through the bites of infected mosquitoes. People who have malaria usually feel very sick with high fever. Data set consists of blood smears for malaria, and the source was obtained from the above link. So this data set consists of two classes, the normal images and infected images. Under methodology, we did do data pre-processing. This involved image resizing. Image resizing helps to reduce on a high computational resources. It also helps to have a fixed size inputs that is required by the deep learning models, and this also helps to eliminate biases within the model. So also having images of varying sizes will introduce inconsistency in the feature extractions. So resizing also ensures uniformities and also improves model performance. So we also do the shuffling of data sets, that's the images. So shuffling is the random rearrangements of the images within your data sets. So this helps to improve overfitting. That is to say, if data sets within the class is arranged by a class, model may tend to learn temporal or positional dependency rather than generalizing the features of malaria-affected cells. It also helps in avoiding biases within the model. Take an instance, if you have images from the different parts of the country, that is from the different districts appearing together in that order, so this will create a bias within the model. So by shuffling, images from different districts will be mixed up in order to eliminate bias within the model. So we also did image augmentations. This involves rotation, resizing, and horizontal flips within in order to create a variation within a data sets. The rotation normally allows the model to run from multiple viewpoints. This helps to improve on generalization capabilities. The red blood cells that may appear in a different orientation. Resizing also creates consistent dimensions, thereby ensuring consistency in the model input. Horizontal prefs helps to create an image that will mirror an original image horizontally. This helps the model to understand features from the different viewpoints. So the class distribution, one represents the affected images, then 0 represents the uninfected images. So under the feature correlations heat map, as seen from the graph, energy represents the correlation of energy with the label. It gives us 0.52. This indicates that there's a presence of malaria within the cells. So low energy normally indicates presence of malaria. Then also, if you look at the homogeneity, the correlation of homogeneity with the label, this is 0.44. This low value for homogeneity also represents the presence of uninfected malaria cells. So high values would indicate that these cells are very normal, since there is homogeneous texture or within the cells, or the cells are very smooth. Then the angular second moment value is also 0.53, which is negative. This also represents presence of affected malaria cells. So the high value would indicate that these cells are very normal. Then the standard deviation intensity is quite high. This high value indicates that the cells within the cells are infected, since there is no uniformity within the cells. So these cells are dispersed from one another. So this would indicate the presence of malaria within that cell. Then when you look at the feature distribution, energy and SMS, they have the same distribution. So from this view, eliminating one, we shall be able to eliminate one feature, since these two features speaks to the same characteristics. Then contrast does not strongly differentiate between the affected and unaffected malaria samples. Then under feature importance, as you can see that SM and energy are the most influential features. So these two, we shall have to eliminate one and remain with one, since they have the same feature importance. Then when you come to the visualizations, you see that there are distinct regions where the infected cells and uninfected cells are clustered separately. This indicates that features do hold useful information for classification. So the extracted features such as the entropy, energy, and SMS, SACM plus standard deviation intensity, these features are very useful for distinguishing infected cells. As you observe, there are also regions where parasites and infected cells mixed. These regions here, infected cells and the infected ones, they mix. So this indicates that some cells share similar texture characteristics. So for us, in order to be able to differentiate these two kinds of classes, we shall have to apply deep learning models that will help us to be able to distinguish these cells that are mixing, like you have here. You have a blue and red. So the aim is to be able to effectively be able to separate these classes from one another. So that's all about our presentation. Thank you for listening. Welcome questions.